Here we're going to look at continuity on an interval, and what I'd like you to do first is, knowing what you know so far about the fact that in order for a function to be continuous on an interval, it has to be continuous at every x value in that interval. And just be careful looking at endpoints, whether they're open or closed. So what I'd like you to do first is just go through and say yes or no to the question, do you have continuity, or is this function continuous on the given interval? And then I'd like you to turn the video back on again. Compare your answers. If you disagree, try to figure out first why your answer is not the same as mine, and then I'll go over it in the video as to why something is continuous or why it's not. So check your answers, see if you agree. Pause the video if you disagree on any of them and try to figure out why your answer doesn't match mine. Then start the video up again. Alright, let's look at number 1. Is the function continuous on the interval from 0 to 1? And notice 0 to 1 is closed. So I look at the endpoints. The endpoints are both the function values exist, and they are closed. It's basically closed there. All the points in between and the interior are also continuous, so this function is continuous. Now when I go from 0 to 2, I now have issues because I have 2 included in my interval, but the function value does not exist. So since f of 2 doesn't exist and we have included it in the interval here, then this function is not continuous on that interval. Now for number 3, since we have left 2 open, then f of 2 doesn't have to exist. It's not part of this interval, and so the function is continuous on 0 to 2 where 2 is open. When we go from 2 to 3, we're also okay. 2 is open, and so even though the function value doesn't exist, we're okay. We have closed at 3, and the function value does exist at 3, and for all values in the interior we have continuity. Number 5, from x equals 4 to x equals 6, since we do have issues at 4 and 6. The function's not continuous at 4, it's not continuous at 6, but since those are not included in the interval, then we have continuity. Basically they're asking us, is this function continuous at all the interior points on this interval from 4 to 6, and the answer is yes. Now as soon as I close in 4, I have an issue because 4 is included in my interval, but there is no function value at 4. So the answer is no, because f of 4 does not exist. And any time you say no, I will be asking for an explanation. Alright, so on the interval from 6 to 8, we have continuity at 8, and 8 is included, so we're fine. At 6, we do not have continuity. And so I'll state the reason why. Now the function value exists. We do have a function value at 6, but it's not equal to the limit. So this would be the reason why. The limit as x approaches 6 of f of x does not equal f of 6, and that's why we are not continuous on this given interval, or the function is not continuous. And then the last one, from 6 to 8, as soon as I open that 6, I'm fine. I'm no longer including the endpoint where I have a point of discontinuity in my function, and so the function is continuous on the open interval from 6 to 8. Alright, if you go to the next page, I'd like to look at some properties of continuous functions, and they really are they make sense. If two functions f and g are continuous at an x value, x equals c, then the following are also continuous at c. The sum of those two functions, the difference of those two functions, the product. The quotient would be continuous as long as the denominator did not equal 0 at c, and that makes sense since you cannot divide by 0. If you took a function and multiplied it by a constant, that would not affect the continuity. Okay, now we have the following functions are continuous at every point in their domain. And so when you think of domain, one of the reasons why we leave values out of a domain is if the function is is a quotient, you have 0 in the denominator, also with logarithmic functions. But polynomial functions are continuous for all values in their domain, but also polynomial functions are their domain is all real numbers. Now for a rational function, the domain is all real numbers such that the denominator cannot equal 0, and so it also is continuous on its domain. A radical function is continuous on its domain, so basically the only place where this function would be considered not continuous would be values that are not in its domain. Same thing for trigonometric and logarithmic functions. Alright, let's look at example 3. It says to state any values of x for which the function is not continuous, and is there a vertical asymptote or a hole at that point of discontinuity. So we know that rational functions are continuous on their domains, and so basically what we're trying to do is find out what values are not in their domain, and we also want to characterize these values as either a place where a vertical asymptote exists or a hole. So the first thing I'll do is I'll factor. Okay, so the first one here, when I factor this, I have no common factors, which means there'll be no holes, but I do have two vertical asymptotes, and those vertical asymptotes occur at x equals 3 and at x equals 4. So these are just the two values where this function is not continuous. It is continuous everywhere else. Right? These are vertical asymptotes. So I'll look at part B and we'll factor that also. So factoring, I now see that I can cancel the x minus 3's, and so I'm left with the function of g of x equals 1 over x plus 3. So what's happening here is that I know where that common factor was. I have a hole. I know where the remaining factor is. I have a vertical asymptote. So basically the points of discontinuity are x equals 3 and x equals negative 3. But we have a hole at x equals 3, and we have a vertical asymptote at x equals negative 3. What I'd like to do at this point is I'd like to graph the original function, and I'd also like to graph the function g of x equals 1 over x plus 3. So I've typed in x minus 3 over x squared minus 9 in y1. And I've also typed in 1 over x plus 3 in y2, but I haven't highlighted it yet because I just want to graph the original function first. I'm going to do a zoom 6. Right, and you can see this is a rational function. You can see the vertical asymptote at x equals negative 3. And if I trace on the value x equals 3 and hit enter, oops, go back, sorry about that. If I trace on 3, I hit the plus by mistake, and I hit enter, notice that there's no y value. So what's happening here, the calculator doesn't always pick this up. It won't show the hole, but you know it's there. So at x equals 3, there is a little hole that we're not picking up here. So now what I want to do, I want to graph y equals 1 over x plus 3, and I'm going to turn this one on by highlighting the equal sign. I'm going to turn off the original, and I'm going to graph just the second function here. Now that looks almost exactly the same as the original function, but this time when I trace on 3, I get a y value. Okay, and the answer, that's actually the value of 1/6 if I put 3 in here. So the difference between the two functions, the original function that had the common factor in there, is that one of them has a hole in it. So this function right here has a hole because of the common factor. X equals 3 is not in the domain, but this function looks exactly like 1 over x plus 3, only there's a hole. Okay, in the next video we're going to look at the continuity of piecewise functions.